today we're going to have a little history and philosophy of science. So my PhD was actually in history and philosophy of science. So and then I kind of went native and more or less became a scientist, but as opposed to like studying scientists. But I think it's worthwhile going back in time for a little bit to try to sort of see where MRI came from. And there's one good reason to do this is that often, a scientific advance is made, but people don't completely understand exactly what the meaning of it was. They understand, this is an advance, we can take advantage of this, but they don't really sort of fully understand what they've done. And it takes 5 or 10 years before they kind of manage to process it. And that happened with MRI. So MRI, basically, and there's one other thing, is if you go back far enough, like if you go back 10 years, 15 years, 20 years, it's not very hard to read papers. But if you go back a long time, 30 or 40 years, it's pretty strange if you go back and read early papers, like take papers in neuroscience, go back 50 years and read or 60 years and read an old neuroscience paper. And it's kind of a little strange, because people had different ideas. Ideas have changed. And so it's fun to do if you've got a bunch of extra time laying around, read about the history of science. And so that's what we're going to talk about today. So how did MRI come about? And in particular, this is relevant to understanding how MRI works, because people still talk about frequency encoding, quote unquote frequency encoding. And we'll see that comes from the original idea of trying to do MRI, and it's kind of it's a misnomer. We'll eventually see there is no frequency encoding. It's all the same kind of encoding, but it took a while. It took basically about 10 years for people to really sort of figure this out. So where does MRI come from? Well, it was invented more or less by 3 different people. So one was a chemist, Paul Lauterbur. And then there was another guy, another British guy, sort of a British. He was more like a crystallographer kind of guy, and then there was a third American guy. So Paul Lauterbur came up with the idea. Basically, he was a chemist, and he did NMR, nuclear magnetic resonance. And so we'll talk a little bit about what that is. But I just wanted to tell just a fun story at the start. So he came up with the idea of using NMR basically to make an image, and it was literally just one lunchtime. He sat down, and then he went to the patent office at SUNY, at Stony Brook in New York, and he said, "I've got this great idea. It's going to be imaging. It's non-invasive." And the patent office said, "Nah, it doesn't sound like anything. It's not going to work." So they blew him off. And after MRI got big, 20 years later, they said, well, maybe that was a mistake. Maybe we should have patented it. And so Paul Lauterbur actually never made any money off of MRI. The British guy made some money, and the British guy and Paul Lauterbur got the Nobel Prize. The third guy didn't get the Nobel Prize, but he got money by suing GE. So where does MRI come from? So it comes from NMR. And why is it called MRI? Partly because they wanted to get the nuclear out, because nuclear NMR stands for nuclear magnetic resonance. And so what is nuclear magnetic resonance? Now, back in the Paleolithic, in this 1975, when I was taking organic chemistry, I learned how to read NMR spectra. And so let's just talk about what that is. And so basically, it's a way of sort of measuring what's called sort of chemical shift. And it's chemical shift in the resonant frequency atoms. And so it's a way of, so what is that? That's small displacements in the frequency of resonance, like the kind that we record for MRI, frequency of resonance due to shielding properties, shielding from nearby atoms. So the idea is that if you have an oxygen nearby, a chemist would call that an electronegative element, and so that one is going to disturb the local magnetic field that's sort of coming in from, say, like, the main coils in the superconducting magnet. And the result will be that the resonant frequency will change a little bit. It's not a lot. We're talking like parts per million, so it's a pretty small change in resonant frequency. And so let's just take an example, the simple example I always give, like acetic acid. So acetic acid has, it's got several different kinds of hydrogen. Here's the acid part. This is a carboxyl group, and then it's attached to a methyl group. And so there's two different kinds of hydrogens here. There's one hydrogen that's near the oxygen, and then these other hydrogens are near the carbon. And so these guys will have slightly different, the hydrogens will have slightly different resonant frequencies. One thing to remember is that what we typically most of the time do in MRI is just look at the hydrogens. And how can we do that? Well, the resonant frequency of the carbon is completely different. The resonant frequency of the oxygen is different. So for any given Tesla. So at a given Tesla, you'll have a resonant frequency for the hydrogen, but you're going to get a completely different one for phosphorus or carbon or oxygen. It will be subject to the same constraints, like if you turn the field up, the resonant frequency will go up. Turn it down, the resonant frequency. So that's exactly the same, but the actual number is different for all these. And so we'll just look at the hydrogens. And so if you now want to measure the resonant frequency, how did they do it back in the day? NMR, the NMR days. And we're talking like this was already done like by 1950, 1960, a long time ago. So the way they used to do it is they would slowly change the frequency, over time of the RF. And so you just ramp up the frequency. So just go like that, and then look for a signal coming back. So, and you can compare this to, like, say, if you had a bell and you had a speaker next to it, and you slowly played some frequencies out of the speaker that changed frequency. What would happen when you got to the resonant frequency of the bell would start vibrating and making noise. And so that's how they started, in the early days, started doing that. Or you could just turn on a given frequency, take a measurement, turn on another frequency, take a measurement. But you can also just turn it on and take measurements continuously. But then they figured, early on in the business, that takes too long. So let's do something that's more like hitting the bell with a hammer. And so what we'll talk about this in more detail. But what is the equivalent of hitting the bell with a hammer? So that would be a very short RF pulse. So here's the input. So that's the input. So if we do a short RF pulse, and what does that mean? It means we just turn on the transmitter at a height at 123 megahertz just for 20 microseconds, tiny bit, just like a little burst of of the transmitter being turned on. So that's the RF pulse. So it's only got one frequency in it, but it turns out that if you make an impulse, just like hitting the bell with a hammer, or just turning on a blast of frequencies for a very short period of time, that effectively contains all frequencies. And we'll, like I said, we'll go over this in detail. But when you have an impulse like that, it's basically like stimulating the system with all frequencies, or almost all frequencies. And so what happens if you do that? Well, you get a signal out. And so what does that signal look like? Well, it's got a whole bunch of different oscillations in it, but it's going to have multiple frequencies in there mixed together, because you've got some hydrogens that are next to the oxygen, other ones that are next to the carbon. And so what do you, and that makes it a little harder to fish out the response to different frequencies that you would have gotten just by slowly ramping the RF pulse, the RF pulse frequency. So if you just like turn on the RF and slowly ramp it, then you can separate the frequencies. Here they're mixed together. And so what did NMR chemists do from the very beginning? They did a Fourier transform. So you've got two frequencies in here. For example, two similar frequencies mixed together. So you got two similar frequencies and they're mixed together. So how do you separate them? Because we hit them with a hammer and did everything all at once. Well, you do a Fourier transform. And so what is one way of thinking? We're going to go over the Fourier transform very slowly, but what's one way of thinking of the Fourier transform? You can think of it as it takes a sample. So this is a sample over time. It takes a sample over time and it decomposes it into the different frequencies that were present, the different fixed frequencies that were present over the whole time over which you did the Fourier transform. And so if you do that Fourier transform, what you'll get back is a spectrum. And the way chemists do this, they sort of plot it backwards. And they plot it in, bizarrely, they plot it in sort of parts per million shift. Below the resonant frequency of just a bare hydrogen. So you could get something that's like a bare hydrogen or some chemical that has the hydrogens in such a place where they're not affected by the other atoms very much, and then call that zero. That sort of sets your zero, and then we're shifting the resonant frequency down because we're shielding. This is like the shielding that we're sort of shielding from the B0 field. So what will happen? You would get when you do your Fourier transform, you get this spectrum, and you get, say this is 12 parts per million, and this guy is about 2 parts per million. So it's a small change in the frequency. And so this guy, parts per million shifts. So this guy's a spectrum, meaning like a spectrum of different frequencies. So this is basically frequency. It's actually sort of delta frequency, like change in frequency, offset, frequency offset. So that's the basic material of NMR. And so like in 1970, I was, it would give you one of these things, and they would say, like, what chemical is it? And then you would try to sort of work through, like, how much is the offset? How, like, you can see that this peak here, this guy is bigger. There's more area under the curve than this peak. And, this basically are the three, methyl ones. And then this is the one, carboxyl. this one guy over here. And so there's 3 of these guys and one of those, that it makes a bigger peak. Now, this is a little more complicated than this. So it turns out when you record this signal, what you're recording isn't the rapid oscillation. Instead, you go through something, which we're going to talk about on Monday, called phase sensitive detection. And these are one of the things that the physicists say, like, we can't tell the psychologists about this because they'll never get it, it's hopeless, but you actually have to understand this in order to understand anything about how MRI really works. And so we'll talk about it slowly. It's pretty simple. But basically what it is it's a way of getting a complex valued signal out of a real signal. So this signal is basically a real signal because you've got a coil and you just have a stream of numbers coming out of that coil. That's the stream of numbers coming out of the coil, voltages coming out of the coil. But it turns out if you do phase sensitive detection, what it does, it will give you 2 numbers, a real and an imaginary number, out of that one stream. So this is one stream of numbers, it turns it into 2. And it does 2 things. So one of the things, it turns it into 2 numbers, but the other thing it does is it just gives you the frequency diff. So, get frequency offset. So it doesn't give you so at 3 Tesla, this is like 123 megahertz. 2 similar frequencies, that are about 123 megahertz. So they're, pretty high frequencies. This thing is just going to give you the frequency offset. So that's only going to be, 2 millionths of 123 megahertz. So that's a much lower frequency. Still a frequency, it's still an oscillation, but it's a much lower oscillation. It's just an oscillation that represents the frequency difference caused by the shielding. So what is the actual signal that you get out of this? Well, let's imagine that we had 2 different frequencies in there, and so because of the 2 different kinds of atoms. And so what would that signal look like after we've just looked at the frequency difference, not the actual 123 megahertz? And so what that would look like, it would look like something like there'd be a signal, like a low frequency signal in there, and then there would be a higher frequency, not much higher, but let's just make it like this. So that's much less than 123 million cycles. So this is, this is time. So this is our, low and high shift. And a difference, it's a negative difference, whatever, but it doesn't matter. It's just this is more of a shift. And so that's the signal. That's the actual raw signal that's that your phase sensitive detection is detecting. But then, so these guys are added together to generate this signal. But the phase sensitive detection also has this real and imaginary part. So let's just look at, let's say this is the real part. So the real part's going to have, it's going to have that high frequency signal in it, and then it's going to have some of the low frequency signal at the same time, like that. So you'll get some kind of, pattern like that. It's got you can do this in MATLAB. Just add a couple sine waves to each other and see what it looks like. It'll look like some funny mess like this. Two frequencies in there. And there's going to be another stream of numbers. That's the real one, but there's an imaginary stream of numbers that'll be different. So here's the imaginary one. We'll just draw that one in there. So we got an imaginary one in there too. It's going to look relatively similar. And what is what is that? Well, that's at any one point in time, So take this point in time, you'll have two numbers. You have a vector. So there'll be like, some vector like that. And there's the imaginary part, and here's the real part. So what is this thing? So what is that thing up there? That's just one number. And so what the chemists were doing this in 1950, doing it with adding machines to do the Fourier transform. So they actually just take the amplitude, and so that's what's actually being plotted there, just the amplitude of that complex number. So it's just like, what is the strength of that complex number? There's an angle of that complex number also. We just threw that out. So there's the phase angle of that complex number, but we just tossed it. And so this thing is the amplitude spectrum. That's why it's called the amplitude. It's just the strength of each complex number. So, what does this? The Fourier transform does this. We'll talk about it in great detail. And it takes a set of complex numbers and turns it into another set of complex numbers. And then we can do, so you start off with, real and imaginary here. And then you get real and imaginary. And then you can do various things with it. So we started off with real and imaginary. We did a Fourier transform, and then we just found the amplitude, the length of the real of these complex numbers. And then we got one number, and then we plotted like how much of this frequency was there and how much of that frequency. So that's the way NMR works. So if you have these different resonant frequencies of the different atoms, and then we do phase-sensitive detection to find the frequency difference, but the frequency difference is still an oscillating signal, and so there'll be like a low frequency difference here and a higher frequency difference here. Those things are added together into this signal over time, and then we do phase-sensitive detection on it and get two numbers out of it, which we'll talk about on Monday. Now we've got a set of complex numbers, and we run a Fourier transform on it to try to figure out what frequencies it contains. And when we do that, we find it just contains basically two frequencies, plus there'll be a little noise at other frequencies, but the signal will come out something like that. And then from that, you can sort of like figure out chemicals. So that's basically where Paul Lauterbur was. This is what he did for a living. So now, how do you get MRI out of that? So one, lunchtime, he just sat down and said, well, maybe we should turn on a gradient. And now you might wonder, like, did they have gradients? Yes, they did. They had gradients from the very beginning. And what did they use the gradients for? They use the gradients for the problem that whenever you stick a sample into the NMR machine, what happens is it disturbs the local magnetic field. So not only did they have gradients, they had sort of z-squared gradients and, x to the third, y gradients. They had all these different gradients for essentially trying to flatten the magnetic field inside the NMR machine. And the first thing you do when you do an NMR measurement is you stick a sample in there, it disturbs the magnetic field, and then you sit there and tweak all the gradients and all the other little shims in order to get the field as flat as possible before you make your measurement. Otherwise, your measurement's not going to be very accurate. And so they had gradients already, and a gradient would just be like a ramp, a linear ramp in the strength of the z component. Chemists, NMR magnets are always vertical. They put them vertical like that. So here's the bore, and so the z direction is actually up so a human MRI, they took that and put it on its side instead because it's kind of uncomfortable to stand. But if you actually look at what they do, they were constantly using gradients. And so Paul Lauterbur just one lunchtime literally said, oh, if we just turn a gradient on, then what will happen is we will change the resonant frequency in a spatially dependent fashion. So turn it on sort of on purpose during the measurement. So, because normally what happens with the gradient, you just put the gradient on, you're just trying to flatten things. You're not trying to actually cause an actual change in the resonant frequency. You're just trying to sort of make it, maybe it sort of like went down a little bit, and so you turn the gradient on, slightly the other way to cancel that out. And then with the goal being that you're trying to get it as flat as possible. But Paul Lauterbur just said, like, why don't we just turn it on and mess it up, Like first flatten it out and then turn it on while we're making the measurement. And then what should happen is we'll get different frequencies coming out of different locations in space. That's basically the invention of MRI. That's why they call it frequency encoding. But it turns out that's the wrong way to think about it. And so let's just go over the analogy. And so what is this? This is basically an analogy between spectroscopy and imaging. And many advances in science come from analogies. And the one I always talk about is the idea of biological evolution. That's an analogy, like the Darwin's Origin of Species. The whole book is one giant analogy. And what is the analogy between? It's an analogy between artificial selection, which is people, breeding animals and plants, and then something similar that might be happening in the natural world, just by selecting different animals. So it's basically like a book-length analogy. And this is an analogy here also between NMR chemistry and imaging, but let's just go over it. So it's an analogy. So basically, we have sort of chemical shift from shielding. Leads to change in frequency. So that's on the spectroscopy side. So here's spectroscopy, and then here's on the MRI side. We got the nuclear out now. So on this side, the gradients cause change in frequency. They do. You turn the gradient on, and so that's perfectly good. And now let's stimulate with broadband. Frequencies, same. So now we time sample the signal. And we do phase encoded detection, blah, blah, blah. So, phase sensitive detection, PSD. And we do the same thing in MRI. And now the final thing. So we do a Fourier transform, which the chemists were already doing, FT, to get spectrum of frequency offsets. The one that was up here, and then in MRI we do a Fourier transform to get object. To get object space. So here's the problematic one. So there's the bad one. Now it is true, we are doing a Fourier transform. We are doing a Fourier transform like just like the NMR guys were doing when we make an image. But conceptually, it's really fundamentally different. And this idea that you're doing a Fourier transform in order to separate the different resonant frequencies, that part is not right. And we'll see why it is. And so if we let's make a box here of sort of our 4 conditions. Okay, so here's the signal that we're getting out of our sample or our brain, and here's the result. Like we want to get a brain image, and here's the spectroscopy side. Here's the MRI side. So just to see why this analogy isn't correct, so let's, what do we have on the, so here we have time domain oscillations. So these are, time domain oscillations from our sample, and then from sample, and then what do? We do an FT. So here's an FT, Fourier transform, and then we get our shift spectrum, frequency shift spectrum. So different frequencies. So what's going on in MRI? Well, what's going on in MRI is what's actually conceptually going on is we have samples of spatial frequency. Frequency, not something that's not like time. So what is, let's just take a second out, what is spatial frequency? Well, spatial frequency, say you have a brain, like a picture of a brain. Okay, and it's dark in the back, and the brain is light. So what is spatial frequency? It's just some kind of sinusoidal variation in brightness. So if I go across the image in that direction, just take a line across the image, what does that line look like? Well, it looks like, it's dark, and then it's light, and then it's dark. And so what's an example of a spatial frequency? So an example of a spatial frequency in an image would be something that's, actually, I made it, it's the other way around. Let's make the brain light. So here's the brain. So the brain is light, and sorry, and the background is dark. So what's an example of a spatial frequency? A spatial frequency might be something that looks like it's really light here, and then it gets a little less light here, and a little less light here, and then it gets dark on the edges. So what does that look like? Well, that kind of looks like, if we make a line across it and just plot the brightness, it looks like a negative cosine. So that's like, like negative cos. And what spatial frequency is that? That's spatial frequency 1. So that's there's one hump of brightness, and you could imagine, well, we could have spatial frequency 2. So spatial frequency 2 would be, something to look like that. So that's, so this is, frequency equals 1. This is, frequency equals 2. So that's what we're actually measuring, spatial frequency. And we've got several things going on here. We've got space, time, temporal frequency, and spatial frequency. And so we have like, so normally when you think of a Fourier transform, you often think of a time signal, like some signal coming out over time, like an audio signal, and you're doing a Fourier transform of turning it into frequencies. So, we turn, time into frequency, and a Fourier transform does that. And the inverse Fourier transform does the other way. It takes a frequency and turns it back into a time. So what are we doing in MRI? We're not really recording. We're recording some samples over time, but it turns out that's not critical, and I'll show you why it's not critical that you record the signals with both frequencies on at the same time. So what we're doing in MRI is kind of the reverse. We're collecting data over here in the frequency domain, so spatial frequency. And then we're doing an inverse Fourier transform to turn it back into space. So space is like time. So this is temporal frequency. Just write it out. So this is an ft minus 1. So that's actually what we're doing in. Now, it just happens to be the case that the forward Fourier transform is virtually identical to the inverse Fourier transform. It's a strange sort of symmetry. So if you take something and Fourier transform it, and then Fourier transform the result, you get back to the beginning. There's just a sign difference. The actual operation is identical. And so it just happens to be the case that we did do a Fourier transform when we processed our MRI data, but what we should conceptually think of this as the reverse, essentially taking some spatial frequency samples and then inverse Fourier transforming back to space. And so if we sort of fill in what's going on over here, so here's our spatial object. But how do we get that? We did an inverse Fourier transform, ft minus 1. And so really, so this is, this is frequency over here, there's frequency over there. These guys are the same kind of thing. And here's time over here, and time is like space. And so why am I hammering away at this? Well, let's just take a look at how the data is typically recorded when we're doing an MRI experiment. And we'll take two different situations to show that the idea of collecting a signal over time with multiple frequencies in it is not relevant. It's not relevant to MRI imaging. So, and you shouldn't think of it this way. And this is the way that any kind of basic MRI course will always present it to you. And then you're on a garden path. You're stuck on this garden path, and you can't understand how it actually works. So let's just look at the simplest kind of MRI experiment. So here's the RF input. And that's the sync function. We haven't talked about that yet, but we'll talk about it. So we turn on the transmitter in that sort of shape, which gives us some band of frequencies. And there's time going over there. And then at the same time, we turn the gradient on. So let's turn this gradient on. And so what is this? This is, the strength of, say, x gradient. And so what does that mean? If it's the x gradient, it means that it's slightly changing the strength of the B field, the z component of the B field, as you move left to right. So, if you're looking at somebody's head in there, like the right side of their head is resonating at a higher frequency than the left side. Now, you might think, well, That sounds good. You've got multiple resonant frequencies in there, and then we record some data over time, and we do a Fourier transform, and that sort of figures out what the frequencies are. That's the wrong way of thinking about it. And why is that? I didn't put the last thing is record data. So it is true, we record data across time. And so at this point in time, we turn the gradient on for a little bit like that, and then we record some data, and then we record some more data, leave the gradient on and record some more data. So we get a whole bunch of samples of data across time. That is across time. And so it kind of looks like this original thing. We've got multiple frequencies coming out, these resonant frequencies. We find the frequency difference, but there's still two different frequencies in there, and we do a Fourier transform to fish them apart. So why is that not relevant to MRI? Well, here's another way of doing the experiment. We turn on the RF, and then we turn the gradient on just for a little bit of time. So we turn the gradient on for a little bit of time, and then when the gradient is off, we record a data point. So there's no multiple frequencies going on because you turn the gradient off and everything's back to same resonant frequency. Then we turn the gradient on again, and then we record another data point with this frequency is all the same. So that's not an efficient way to collect your data, and you'd get some decay, but if we just ignore the decay, the data would be the same. So amazingly, this is the same. So that shows you that same data, except for decay, But we don't get it wouldn't change the nature of the data except decay. So same data. So think about that. What it says is that in this case, you're recording samples over time, and you've got multiple because you've turned the gradient on, you've got multiple frequencies going from left to right in the head. So like the right side of the head is resonating higher frequency than the left side of the head. In this case, that's not the case. You've turned the gradient on, and for a while, the right side of the head resonated faster, but then you turned it off, and then you recorded a sample of data with all the frequencies the same. And nevertheless, it will still work. And so that shows you that the idea of trying to separate the frequencies by that are simultaneously present in the signal by doing a Fourier transform is not how it works. It fundamentally is not how it works. Now, certainly you affected the system when you turned the gradient on. That did something to the system because, the data is somehow the same. But what it didn't do was make a signal over time that contained multiple frequencies, because the frequencies are exactly the same at all these points in time. So that shows that we're basically not recording a time domain sample of oscillations over time. What we're doing instead is we're recording samples of spatial frequency, individual samples of spatial frequency. And this realization of how MRI actually works took about 10 years to kind of sink into the field. This was the idea of K-space. K just stands for frequency. So what does K-space mean? K-space just means frequency, spatial frequency. It just means frequency space. And so, like I said, it took about 10 years for people to sort of like munge through this and realize, we're not actually doing the same thing, even though that's how it was invented. And even though it's still called frequency encoding. It's still taught this way to confuse psychology students. But it's not frequency encoding. It's not temporal frequency encoding. It's setting up your brain in such a way that you can record multiple spatial frequencies. It's kind of the inverse of nuclear magnetic resonance. So, and so this happens a lot. So the other example I often give is like you're still stuck with this sort of frequency encoding name. You still have the frequency encoding direction. We'll see there is no frequency encoding. It's all phase encoding. But if you look at another field like molecular biology, in molecular biology they had this concept of protein translation. So where does so you have DNA, and then you do what's called transcription. That because that sort of just makes a copy, like a mirror copy of the DNA information, and then this part's called translation. To make protein. And so why is it called translation? Well, when they were first thinking about this, about how this works, they had this idea that it was kind of like the Morse code. That was like the original idea. And so you were translating between like, the Morse code and a letter. And it's an incorrect analogy even for that, because if you think about it, that's not translation. That's just kind of encoding something. But the idea was that it was kind of a metaphor, like we're translating between the two languages, like the RNA DNA language and the protein language. It's not that's not the way molecular biologists understand it now. How do they understand it now? Well, we're sort of like getting, this thing is some code and we're getting the meaning out of that code. The protein is kind of like the actual meaning that comes out of this encoded string. That's the way molecular biologists think about how it works, but it's still called protein translation. and that's like frequency encoding. It's still called frequency encoding, even though it isn't. So, okay, so let's just, any sort of general questions? So the overall overview is chemists were already using gradients to flatten out the field, and they collect a time domain signal, a bunch of time samples that contain multiple resonant frequencies. They actually do contain multiple resonant frequencies coming from these atoms that are shifted because of whatever the nearby atoms are doing. And so the original idea of MRI was, why don't we just turn a gradient on, and that gradient will cause different frequencies in different parts of the sample, and then if we do a Fourier transform, we can sort of fish out those different frequencies and figure out where space is in the sample. But in reality, what's going on is, as you can see from this example, is what you're doing is you're actually recording spatial frequency samples. So you're recording, like, how much does the brain look like a cosine? And to do that, it doesn't require that you have multiple frequencies on at the same time. So that's fundamentally not how it works, because you get the same data here if you record all your data points with the gradient off, meaning the frequency of all the oscillations is exactly the same. So this K-space sort of, Copernican K-space switch, where you change from, sun going around the Earth to Earth going around the sun, it's that what we're actually doing here is recording these spatial frequency samples, a frequency domain thing, and we're turning it back into a spatial thing, which is kind of like time. And it's not like spectroscopy, where you really are recording multiple frequencies over time and using a Fourier transform to fish them apart. Now, you might have heard of MRI spectroscopy. So it turns out you can do this at the same time as you're doing this. It's possible. We'll talk about it later in the quarter. So it's possible to get a spectrum of frequencies coming out of your sample in addition to doing an image. So it's possible to do both of these at the same time in a tricky way. So you can do spectroscopy just like the chemists did, but basic neuroimaging, reconstructing an image, is kind of the inverse. It's kind of the inverse of spectroscopy. Okay, so I don't know if this was helpful, but just to sort of get an idea of like how MRI started. Any questions out there? Anybody looked at an NMR spectrum? Anybody take organic chemistry out there? Okay. Yeah, there you go. Yeah, I mean they use spectroscopy for doing. You can look at like protein structure in solution instead of like the way the protein actually is operating. You can do NMR on an actual protein. There's a lot of work on that. Well, they do. So, like, they do change the frequency, like during this period of time. So they definitely do. And you have to put the gradient on, and what it's doing to the spins is totally critical for making the data points be the same. The only point here was that your intuitive way of thinking about this is you put a gradient on. It causes this different frequencies to appear at different points, and then you do a Fourier transform to sort out those frequencies. And it is true that you do a Fourier transform, but it's an inverse Fourier transform. And if you do the experiment this way, you can see that you're collecting data over time, but it doesn't matter that all the data you collected was collected with the gradient off, meaning the frequencies were all the same. So each one of these data points was collected with essentially no change in frequency across the sample, and yet you still get the same data. So it requires that you turn the gradient on and cause a change in phase. You basically caused a change in phase of the oscillations, and then you turned it off, and then they went back to oscillating at the same frequency. And the fact that now their phase has changed is critical. It's critical that the gradient is on. But the part that the garden path is, don't get this idea that when we turn the gradient on and record a signal that contains multiple frequencies, that we're fishing the frequencies apart by doing the Fourier transform, because that's actually not the way it works. But like I said, it took 10 years for the guys who were doing this, to actually understand what they were doing. And a lot of science happens this way. You get an idea, you even like raise some venture capital and make an MRI company, doesn't matter, even though you don't really understand how it works. You don't really understand how it works, and then later on you finally get it through your head, like, what are we actually doing? That a lot of science has this a little bit of a sleepwalking feature to it. Like you get this idea of the scientist, I'm making a hypothesis and I'm testing it. And I say, yeah, you occasionally do that, but that's not how you really make progress. You really make progress by going out on a limb and then doing something that's kind of really wacky, and then maybe understanding it well, like 5 or 10 years later. Okay, so I think we'll end there, Stan, before I go over.